Good afternoon, everyone. Welcome to our very last class of this series. I know you're all saddened by that news, and we're going to miss doing this and not seeing, but watching you all chime in and ask amazing questions. So we're so grateful to everyone who joined us throughout these last 7 months. Has it been 7 months, 6 months?
Has it been that
Oh
long?
my
I
gosh.
thought it was
Wow.
3 Sunday.
Yeah, no,
Time
no.
flies.
It's been wild. It's been a wild ride, but
Yeah.
thanks everyone. We appreciate you. Today we're going over commercial water heating. We are recording this session, so you will get a copy of it sent to you early next week. If you have any questions throughout the class, you can use the chat function or the Q&A function. They're both at the bottom of your screen. I will be monitoring both. We will take all questions at the end of the session. We'll have about 15 to 20 minutes once Paul gets through. And with that, I'm going to hand it off.
Awesome. Thank you, Sunday. Yeah, as Sunday said, listen, thank you guys for joining us. We always appreciate it. And we're hoping to maybe take a break for the summer. So I think everybody's maybe excited about that. Probably nobody more than myself, but yes, thank you guys. I'm going to turn my video off if that's okay. I think we'll kick that back on as we get into questions. Let's see if we're still doing, we should still be doing okay here. All right, technical problems, but I think we're doing all right. Let's get going with commercial water heating. We just want to review a couple options for you as far as heater selection and choices. Also some sizing fundamentals, if you will. At the end here, I've got a little example of a multi-unit apartment building, and we'll look at some various options and how they price out and why you might consider one option versus another as far as getting into water heaters. Okay, so let's get rolling. Hope everybody's seeing my screen as I'm advancing here. So I hope that's working.
You're good, Paul.
Thank you, Sunday.
Mm-hmm.
When it comes down to sizing, you're going to get a lot of, or water heaters in general. To me, boy, this is one of the most confusing things we need to deal with. There's a lot of things that get thrown at you, a lot of terms, hourly demand, occupancy types, Hunter's curve, modified Hunter's curve. You're like, holy smokes, there's nothing easy about it. Um, okay, let me launch my first poll before I get going too far here. We'll let this one stay up for a few minutes. It's just to test how many of you are long-termers versus maybe attending a few of these. So let me keep going as far as terminology goes. So you're going to hear about different building types, hours of operation, venting requirements, footprints. There's a lot that goes into selecting water heaters. Ultimately, owner decision is another one that really has a lot of power as far as what they want to see inside their building. If you're looking for reference material, there are some good references out there that can help kind of decipher uh, terms, sizing, and approaches. Okay, so for me, ASPE has some good references. Their CEU 221, domestic hot water systems in general, is a really good overview. Also, they've got a kind of a hardbound manual called Domestic Water Heating Design Manual. It's more for multifamily, but it does a really good job of giving you examples and kind of walking you through various options. And the last one here, I got to hide my poll a little bit, is ASHRAE Chapter 50 that deals with service water heating. I like this one the most. It's just kind of cut and dry, gets right to the point, and they do have some examples in there as well. I'm certainly not going to go through all of these because it's just a lot of information. I think Chapter 50 is a good 25, 30 pages. But if you're looking for some reference material and you want to better understand water heaters and or the sizing criteria behind them, to properly size a project, all good references. For me, you got to be a little bit careful here. If you're backing into sizing, you want to use something that's going to hold up in a court system in case things go wrong. So referring to some professional organizations like ASPE and ASHRAE are safe ventures. Let's put it that way. Versus a fancy dartboard where you say it worked on my last job, so it should work on this one. Yeah, doing some hard calcs is always a good thing. being able to justify your sizing. Uh, Another thing that's out there is manufacturers' websites. A lot of individuals, engineers included, reps included, are using A.O. Smith, and they have some really good sizing criteria there. A lot of people have comfort with their software. So if you go to hotwatersizing.com, you'll end up at A.O. Smith's sizing site for looking at various loads. We're not the A.O. Smith rep, but it's good to know what most people are using as far as backing into sizing criteria. If you're going to go tankless, IntelliHot, we'll talk about that in just a minute, but IntelliHot has some really good sizing on their site too. And they'll actually write you a guarantee letter based on your fixture units and the business type that you enter to stand behind it, to stand behind their selection. Let's put it that way. Okay. I'm going to go ahead and hide my poll. Thank you, everybody, for participating in that. There'll be one more at the end, but other than that, we're good. Kind of short and sweet today. Let's talk about some various options as it relates to water heaters in general. So majority of the business that's out there tends to be tank type, and whether you're doing this at home or commercially, you can do this electrically, where you just have electric elements stuck into the side of a storage tank. All right, and those elements are going to cycle on or off in order to maintain a set point within your tank. So you always have hot water available to you. Another option is going with gas, of course, gas or propane, depending on your venting requirements. Nice thing about electric, you don't have to vent it, but if you're dealing with gas and propane, you do have to get those products of combustion out of your mechanical room or out of your home. You don't want people taking a long nap. So venting can be a bit of a challenge for any gas-fired water heater, something to keep in mind. You'll see manufacturers, I don't want to say play games, but get creative with how they maybe market water heaters. This is a good example, and I'm not trying to push Lochinvar. We're just the rep, and Lochinvar just gets creative. Here's a good example of that in what they call the Shield. Looks exactly like a tank type water heater. If we went to look at recoveries, you'll notice that it's going to be quite a bit higher than a standard tank type water heater and more efficient. You wonder, so what's the magic under the jacket? When you open that up, you'll see that, oh, look at that. They've got a dedicated water heater inside the jacket. And below it, they've got a smaller storage tank and a circ pump. So they are simply circling water back and forth between a pretty good size heater and a smaller storage tank to develop some pretty nice capacities. Okay. So that's, I don't want to say a game, but a convenience in the fact that it looks like a tank type water heater with really good performance behind it. Typical on a tank type though, you're looking at some type, I just wanted to look at this example with Bock. It's a dedicated burner that sits inside the top cap, if you will, and simply sending hot flue gas down the first chamber. And that hot flue gas is hits some turbulators, additional surface area, comes down to this bottom pan and makes a hard 180 and comes back up for a second pass. Again, where it hits a lot of turbulators, and you're dealing with hot flue gas that starts out about 2,300 degrees, comes up to the top here, hits another 180 and comes down these how do I say it, third pass tubes before it exits or vents the water heater. Now, this is typical of most tank type water heaters. They're trying to get as much heat as they can out of this product of combustion. And if you look down at the top here, all right, here's the first pass where flue gas is sending down towards the ground, second pass where it rises up, and then third pass where it gets equally distributed through all these additional surface area before it physically vents the water heater. Okay, and all that's surrounded by a jacket of water, trying to pick up as much heat as we can as we're firing that natural gas. A lot of people ask or maybe get confused by how do you physically size a water heater? So let's talk real quick about a tank type and maybe demystify it a little bit. There's a lot of information on a standard submittal or selection sheet that you might have to decipher a little bit. As far as what size burner you've got, how much storage is available, the efficiencies, is it modulating? And then you got recovery rates. So if you're looking at recovery rates, one thing about water heaters, it's usually in gallons per hour. Everything else we do in the hydronics business tends to be gallons per minute, but water heaters are gallons per hour. So in this case, you'll notice a little 125,000 BTU gas-fired tank-type water heater can recover 144 gallons a minute. Or sorry, gallons per hour. See, there I go again. And if you take 144 divided by 60, that's equivalent of about 2.4 gallons per minute. But most of the time when you're doing sizing, you're looking at hourly recovery. As a result, you want your water heater to be based on hours of recovery, or how many gallons you can recover in that hour. All right. A typical design is 40 to 140, which happens to be 100-degree delta T, or rise, increase in temperature. So most of the time you'll see manufacturers list their recovery with a 100-degree rise. So that's usually the chart you want to look at, or the column you want to look at if you're trying to match a load in a building. You'll also notice there's a column next to that called first hour delivery. Well, what's the difference between these two? One's a little bit higher, and you might be tempted to use this. Be careful here. Recovery is the amount of water we can heat when the burner is firing, and within the first hour, okay, or on an hourly basis. So 144 gallons every hour, and if the burner's firing for 8 hours, 10 hours, 24 hours, it doesn't matter. Okay, you're going to get 144 gallons every hour. This first hour delivery, this is where you need to be a little bit careful. It's taking advantage of the storage that's in your water heater. Now you can't use all 99 or 100 gallons of it, but you could use roughly 70 gallons of it before water cools off enough, and now you're relying solely on your burner recovery. Okay, so most of the time you're selecting your tank type based on recovery alone, not first hour delivery. I hope that makes some sense. The other thing to watch out on tank type is whether you need an ASME code or not. You'll notice that the first three here don't have an A next to them, meaning they're non-code water heaters. You're going to notice that as soon as we get into a unit that's 200,000 or greater, it's got an A next to it, indicating ASME. So if you look at typical code, ASME requirements for a water heater are anything that has a burner greater than 200,000 and storage greater than 119 gallons. So that's kind of your cutoff. So you'll see a lot of manufacturers get their burners right up to 199. So it can be non-code. And as soon as you get to 200, you need to be ASME code. Okay. Why one versus another? You would think safety-wise in a building, you're going to want ASME code. You have some owners that want to utilize non-code water heaters. An advantage for an owner, you don't have to pull a permit to pull or replace it. You also don't have to hire a union plumber to work on it. So you can have facilities work on a non-code water heater where that's not necessarily true if it's ASME. Okay. And I'll get to an example here towards the end. We'll beat that one up a little harder. Let's talk. We've been talking about tank type. Let's take that same storage tank idea and put a dedicated heater next to it, which we would tend to call sidearm, and the fact that we've got a dedicated water heater serving a storage tank. And why are we doing this? Why don't we just take a dedicated water heater and generate our 40 to 140 and meet the load out in the building? Most of the time, this dedicated water heater can't handle that 100-degree rise across the heat exchanger itself. They're usually limited to about a 60-degree rise, which means if you want a 100 degrees rise out of your domestic water, you have to circulate it through a storage tank, okay, or circulate the water that's being held in the storage tank, which is what we're doing. I know I've said this before. I'll say it one more time. Just be careful. We have a lot of individuals engineers, contractors, personnel that will look at this application and say, we've got a boiler serving a storage tank. Be careful with that, because anytime we're directly heating domestic water, technically it's a water heater. So this is a water heater that is serving a storage tank. Okay, that gets confused a lot and creates a lot of pain points. If you see a lot of copper pipe, yeah, you might want to check it out. Probably a good indication you've got a water heater application. You've got different choices for water heaters or sidearm dedicated water heaters. Condensing is one option that's out there for sure, and the other is going to be a non-condensing option. Let me let's see where I'm going here. Let me go back for just a second. One thing we have to think about is if we're storing this storage tank at 140 degrees, what temperature are we going to expect coming out of the bottom of it anytime the heater fires to recover the storage tank? And you might think 40 degrees. Yeah, that's not really the case. The whole time we have 40-degree domestic water blending with that 140 in the storage tank. Ultimately, we're probably going to expect 90 to 100 degrees leaving our 140-degree storage tank headed to our water heater. Okay, now if our water heater is condensing, the colder that water is leaving the bottom of our storage tank, the better. Okay, that's good for efficiencies. But if we decide we're going to use a non-condensing water heater over here, most of the time those have a minimum return of about 130 degrees. So if you're getting 90 to 100 out of the bottom of our storage tank, that creates some real problems for a non-condensing water heater. So how do we deal with that? Because there's certainly both out there. You just need to be prepared for it. How do we deal with a low temperature coming out of a storage tank for a non-condensing water heater? Well, we're going to add something we might call a bypass and in the field, and then some manual ball valves, which we call circuit setters. And that 90 to 100 degrees that's coming out of our storage tank simply rolls into our heater. We heat it up. There's a pump on the back here, okay? And we heat it up. We send hot water back to the storage tank, but we don't let all of it go to the storage tank. We start to throttle this valve, circuit setter B, down. We create some resistance, and we force some of that hot water right back into our return through this little bypass. We can trim it out with circuit setter A, but ultimately the goal is to throttle circuit setter B until we get enough return water that our temperatures start to rise. Once they get above 130, you can lock in or dial in your circuit setters and walk away. Because every time the water heater starts, we're going to get 90 to 100 degrees coming out of our storage tank. Okay, so this is how you would protect a non-condensing water heater. If you don't do that, you got about 6 months and counting before you might have to walk in there and replace it. It doesn't like to work in a condensing mode. Storage tanks. You're going to see some options for non-code. Remember, 120 gallons or greater tends to be ASME. So you've got options for some non-code storage tanks, typically for residential applications. Anytime we're dealing with a commercial building, though, we tend to be looking at ASME just because we have larger storage requirements there. If you're looking at a bare tank, that simply means the external is bare. Internal to the tank, it's usually glass or cement lined. The question is, do you need the tank insulated or not? And if so, do you want the factory to do that? Where you can insulate it either with foam and a jacket around it as round, or doing the same thing as square, or hitting it or spraying it with some foam that's really designed for only outdoor use, not indoor. There is some fire concerns, off-gassing with a bare foam tank. So yeah, we wouldn't recommend you sticking that inside a mechanical room. Okay. The other thing to be careful about is your max working pressure. You can get either 125 or 150, depends where the tank's located. It depends what pressures you're going to be seeing in your domestic side. I mentioned this briefly, but one thing we're trying to maintain in a storage tank is some level of stratification. We're trying to keep our hot water near the top of this tank. And as cold water comes in from our city, it's going to pick up this hot water and send hot water out to our system. How do we do that? Most tanks are going to have some type of baffle installed, and that baffle tries to keep this stratification or turbulence within the tank as low as possible. If you order a tank without baffles, you might get a lot of stirring going on inside the tank that dilutes it pretty quickly. That would simply mean that your heater is going to have to run more often to recover it. But one question that always comes up is how much usable water am I going to have in this storage tank? Let's say it's a 100-gallon tank. Industry standard tends to be about 70%. Lochinvar is claiming 80%. So a 100-gallon tank, we can send 80 gallons out to the system before we have to turn on our water heater and recover the storage tank. So yeah, it really depends on what tank you're utilizing. The other thing is if you lay the tank on its side, it becomes horizontal. That's fine too, but your stratification or your drawdown becomes about 65 to 75%. Okay, it's not as great as it is in a vertical tank. Since we're talking about storage tanks, we're talking about water heaters, I think we also need to talk about this thing we call the tempering valve or master mixing valve. And hang on, I just screwed myself up. All right, okay, I'll get it back. Sorry, technical errors. So what we're calling here is a tempering valve is a master mixing valve. Not point of use, but a master mixing valve in the mechanical room. And all this is doing is taking hot water that leaves our storage tank and blending it with city water, okay, or our recirc water to temper it down safely. So typically we're sending out 120, maybe 115, so nobody's getting scalded, but they still have hot water available. My only caution here is we've seen a lot of individuals take this recirc pump and tie it directly into their water heater, okay, into this leg here, and then have a check valve above it, basically. Uh, the recirc has to be able to serve both sides of this master mixing valve. So you have to be able to have access to the cold port as well as the hot port. So just keep that in mind. Otherwise, we end up with some cold uh, cold legs and some long waits for hot water in the morning. All right, that's our master mixing valve. Now we've been talking about dedicated water heaters. Let's throw a wrench at that and do something we call indirect. What are we doing with an indirect water heater? What are we talking about? We're talking about using our boilers in this case to indirectly heat domestic water. And how do you do that? Well, you're going to you need some type of break, and by break I mean you can't directly take your boiler water and heat domestic. So in this case, our break is a heat exchanger. So we flow hot water, boiler water through one side of the heat exchanger, and on the other side we circulate it back to a storage tank with our domestic water. Just a quick flow schematic of that. So again, hot boiler water is coming into one side of our heat exchanger and back to the boiler plant. It's chemical laden. Our boilers aren't designed for direct domestic water. And over here we have a storage tank with a dedicated pump that is simply picking up heat through our heat exchanger and bringing it back to the storage tank. That works great if you're trying to multi-use your boilers for both building heat as well as a domestic priority. Another way of doing it is having an integral coil inside your storage tank. I don't have a good example of that, but it acts just like a heat exchanger. It's a break. So your boiler water isn't directly in touch with the domestic. Okay. So in this case, you could say we're using a boiler to heat domestic water, but we're using a heat exchanger to separate it. I'm just throwing this out there in case you happen to run into a steam application. There's a few manufacturers out there. Sunline is certainly one that does is very, very good at taking steam and generating domestic hot water with it. You can do that instantaneously. You can also add a little bit of storage here. Basically, this is simply an inverted shell and tube heat exchanger with a stainless shell. The steam runs through the tubes. The domestic water is on the outside of that. So you come in with cold water and you leave with hot water. Design considerations, you need a pretty good recirc system if you're going to do instantaneous or pipe it back to a storage tank. But if you need help on a steam application, glad to do it. It's certainly a dying art, but yeah, anybody at CHC with gray hair tends to have some steam background. Now let's talk about tankless for just a minute. Up till now, we've been talking about tank type. We've been talking about sidearm to a storage tank, and maybe even a steam application. But if we want to get rid of all that and just directly heat water without a need for a storage tank, we're going to call that tankless. Okay, and there's only a few manufacturers out there that can handle the commercial side of tankless. And the reason commercial is so hard is that you get a lot of cycles. Picture a kitchen that's on and off all the time, all day long, and you've got no storage tank to kind of buffer that out. So your heater has to handle all those cycles that are occurring within the building. Um, it, you can have up to 1 million cycles a year in a typical commercial water heating application. So you have to have a pretty resilient system if you're going to go after that. We also don't want to be out of hot water. That's a bad thing on the commercial side. You don't want to shut down a kitchen. That means you're shutting down a restaurant or you're sending all the kids home from school. Okay, not a good thing. So let's look at one example of a commercial tankless manufacturer. And in this case, it's IntelliHot. We rep IntelliHot, so I can talk intelligently about that, or I'll try anyway. But there's a couple others out there as well. But let's just talk about what IntelliHot's doing. They've got a single coil heat exchanger. It's all stainless. There's no welds in it. It simply flexes as that burner comes on and you get flow internally through this coil. So you come in down low with cold water, you leave with hot water, and they're calling this a engine. We might call it a water heater, but they call it an engine. So let me just stay with their terms, which is engines. In this case, they're going to take multiple engines that are usually 200 to 250,000 BTUs, and they're going to manifold them together. In this case, we've actually got 6 engines that are manifolded together. You can see 3 in the front and another 3 in the back. Okay, they make up about 1.5 million BTUs worth of water heating capacity. Pretty slick. It's a single point of connection for the system. It's a single vent run, single makeup air, single gas connection. Okay, and all that happens within this this packaged unit, if you will. The thing that's really important about IntelliHot or tankless in this aspect is the fact that each one of these engines has its own motorized isolation valve and also has its own flow meter. And what's cool about that is if you know the flow in your system and you know the delta T, you can do something we call BTU staging, which means you know exactly how many engines and burners need to fire in order to recover the hot water required out in our system. Okay, so it's a very smart, very intelligent water heater design. Now, when we're just recircling the building, we're going to have a very small load. But as the loads increase, you're going to bring on more engines to recover that. If the load continues to increase, you can start rotating or cycling which engines are going to fire based on how aggressively they fired last time. So they call it masterless control, but basically they're trying to average runtime and aggressive behavior. So they do track that. And if you get to a full load condition, all engines are going to fire. Okay, it's really that simple. And then they stage on and off based as the loads fluctuate in our domestic system. One thing that's been really successful for any retrofit or existing project is going in with a water meter and using that water meter to track the existing building load. You can, what do I want to say? You can forecast that out for 100% occupancy. And you give an owner a really nice report that says, "Hey, I know your water heaters are sized for X gallons a minute, but based on your water meter and 100% capacity, you're not close to that." To right size a water heater is pretty important these days, and that's the power of a water meter. I think IntelliHot's done close to 200 buildings with a lot of various applications, and they're very comfortable with their sizing, also very comfortable with their diversity loads, because they've got water meter tracks to show how that works for various types of buildings. Let's talk about how you might want to pipe a tankless water heater. Notice there's no storage tanks in here. We've got cold water that's coming into this heater on the left first, and then it continues on to the heater on the right second. Okay, and then heads out to the system. That's it. We may have a tempering valve, master mixing valve in the system if you want to add that. We have a recirc pump that's also coming back and flowing through probably one engine and sending it out to the system. The thing that's really important about tankless is making sure we have some reverse return piping, making sure that we have equal flow or balanced flow into our multiple water heaters. Now, if you've got an owner with an existing storage tank and they want to utilize that, or there's a potential for a big dump load, like a big laundry facility, a storage tank does make some sense. And you can do that. We just ask that you kind of put it on the end of our water heaters with options for a couple bypasses or shutoff valves. If we want to prove to the owner that tankless works, we're going to isolate off the tank, open up the bypass, and see if the heaters can track their load. Okay, now if there is a big dump load or some concerns, this simply acts as a big piece of pipe over here. We don't have a dedicated pump circuit to it. Our goal is just to keep that warm. So if there's a big dump load, it can be met off of the storage tank. Remember, we've got a flow meter, and in doing that, we can tell you exactly what the flow is across the unit. We can look at temperatures in and out. We can tell you how many BTUs need to be fired in order to recover it. We can also put out some nice little charts or graphs that show an owner, hey, how much water are you using in an hour, or in a day, or in a week? Okay, so there's some powerful tools behind technology. Also say, how much energy are we using? How hard are we having to fire our engines or our heaters to meet your recovery? Okay, so all that's tankless water heaters. Let's look at another one, if you're still with me. And that's heat pump water heaters. Definitely picking up a lot of traction. How are these guys working? Well, they're using something we call the refrigeration cycle to simply transfer heat into domestic water, and then also take some warm air that might be in our a server room or a parking garage or outside source, to take our refrigerant and turn it back into vapor and continue our refrigerant cycle. So a lot of people talk about a refrigerant cycle. It can be confusing if you don't have any experience on the refrigerant side, like myself. Basically, we just have a compressor sending vapor, hot refrigerant into a heat exchanger. We use a lot of braze plates for this. That hot refrigerant is simply transferring its heat over to domestic water, where it goes to some storage tanks, and then it comes back as a high pressure liquid. At that point, we run it through a metering device and we drop it to low pressure, but still a liquid. And that liquid is looking for some heat to boil it back into a vapor. And that's what we're doing through what we're going to call an evaporator, or picking up warm air from our space. You can also do water to water heat pumps and pull something from your application, whether it's off your loop, ground source, wherever you've got a source for some warmer water. And if you're new to the refrigerant cycle, HVAC School has some great YouTube videos on that. They break it down really simply. I'm a simple-minded person. A compressor is a pressure increaser. That makes sense. Condenser is a rejector. Metering device is a pressure dropper. All real technical terms. And then you could put some numbers to that. And I'm just making up random numbers. But basically, if we're coming off our evaporator at 20 pounds, our compressor might increase that up to 170 to give us the ability to generate 120-degree domestic water. Now, in reality, heat pump water heaters can generate up to 160-degree domestic water. Okay, so they're running much higher pressures, but just maybe a quick look at some sample pressures and temperatures. Let's talk about how these might work in the field. Because if you see a piping schematic like this, you're like, oh, this doesn't make sense. Well, there's too much going on here. We've got multiple tanks, one heat pump water heater, city coming in. We've got a recirc. Okay, this is a head scratcher. So when you're designing a heat pump water heater, one of the things you have to figure out is how often is it going to run, or what's the off peak? Meaning when nobody's using domestic water and everybody's sleeping, that's when the heat pump water heater is doing its job. And what it's doing while everyone's sleeping, it's sending small amounts of hot water into storage tank number 2. It's also backfeeding into storage tank number 1 and continue to send cold water back to the water heater, or heat pump water heater, forgive me. Okay, so throughout the night, an 8 to 10 hour cycle, the goal is to get storage tank 2 and storage tank 1 up to temperature. Now, when there's a load in the morning, people are jumping into the shower and they're looking for hot water. You've got city water that comes in and starts pulling hot water out of storage tank number 1, sending it over to storage tank number 2, and possibly into what we might call a swing tank. And all a swing tank is, it's kind of a final tank to make sure we've got some hot water available for our system in case things go wrong in the middle of the night, or there's a really big load that exceeds our design. So swing tank typically has some type of backup heat, whether that's a dedicated gas water heater or electric coils in there, something to make sure we're maintaining 140 in our swing tank. Okay. Be careful on time. I'm running a little long. So Sunday, forgive me. We've got just a few more and then we'll get into a quick example. If you want to look at something interesting, that might be using that same refrigerant cycle to pull some heat or domestic hot water out of wastewater, believe it or not. There's a technology out there right now that lets you do that. And they are simply using that refrigerant cycle, and they're using waste heat off of our sanitary or sewer that's leaving a building to generate domestic hot water. You're like, oh, gross. But they've got a heat exchanger over here that is that they're going to fill with sewage. There's no contact. It's simply I want to say it, helping or assisting with the refrigeration cycle. And when all that sewage is given up its heat or temperature, they dump it back into the pit or the storage tank. Okay, and then there's going to be an overflow if this gets too full as it's coming in. So it's just one way to utilize sewage as domestic hot water. Pretty slick option. It just needs some design considerations. And there's certainly savings here. But it needs to be part of the early design process because you need a pretty good sized pit to store your sewage in order to transfer it back and generate heat from it throughout the night. If you're into a really big campus, that's another option. I think you've got flow rates here up to about 4,500 gallons per minute. So you're talking about a big campus, maybe tying a branch line off of a city main. There's definitely heat there, and it's just taking advantage of it. So there's technology out to help with that. All right, I've been mumbling along for a while, so let me get to my sizing example, which shouldn't take too long. But I just wanted to look at, all right, somebody throws a multifamily apartment at us with roughly 145 units inside this apartment building. For the life of me, I should have made this a 100-degree rise instead of a 90-degree rise, but all right, just bear with me. We're going to call this a low demand profile, and we're going to assume that there's 2 peaks throughout the day for domestic hot water use. Okay, one in the morning from 5 to 8, and another in the evening from 4 to 7, basically 8 hours between our peaks. That's really important when we get to our our heat pump water heater sizing. So let's go. How would we approach this? Oh, forgive me. Let me launch my last poll and we'll wrap this sucker up. So hang tough. Downsize that. All right. So one of the first things we might want to do is maybe look at some tank type water heaters. Okay, what are our options here? Well, we might go to A.O. Smith, hotwatersizing.com, enter our conditions, 50 to 140, and then we've got a certain number of 1 bath, 1.5, and 2 bath units. We might assume each one has a clothes washer inside of them. And if that's the case, we're going to end up with a peak demand here of 942 gallons per hour. So I need to find a water heater that will recover that. Where are we going to go from there? Well, I don't represent A.O. Smith, so I might go to a product that I do represent called Bock. And Bock makes a tank type water heater. Now I've got some options here if I'm trying to recover 942 gallons per hour. I can go with some non-code units. In this case, I'm going to need 5 of them to give me 942. They come in at a cost of about $8,000 each, or a total of $40,000. I could also be looking at some ASME code versions of the same water heater, okay? Just a little bigger burner on them and a little more storage. Excuse me. Price-wise, I'm fairly close, but it depends on what the owner is looking for. Now, one thing that's important about tank type, typically they cannot be individually or they cannot be combined vented. Normally you're individually vented. So if you've got 5 tank type water heaters, you've got 5 vent runs leaving your mechanical room. Okay, just something to keep in mind. Now I'm going to get to a summary at the end here, so don't worry, don't stress out. Let's look at maybe a sidearm approach, where we're taking a dedicated water heater tied to a storage tank. Now we've got an in-house spreadsheet that kind of takes that ASPE domestic hot water sizing guide and turns it into a usable spreadsheet. So I can plug in that same information we just looked at and kind of analyze it in a spreadsheet form a little bit. And what this is doing is telling us, all right, any place we've got a negative number, we're going to be short of hot water. So that first hour is usually our critical critical to evaluate. Okay, we want to make sure we satisfy this. So what we've done here is we've selected 2 condensing water heaters that produce a total of 664 gallons per hour. But I'm still short 232. Well, how do I make up for that? With the storage tank. So in our case, we're using a 318 gallon storage tank, but I can't use all of it. Okay, I can use about 80% of it, which gets me to 254 gallons of usable, which exceeds my 232, which tells me that this is going to work just fine. Now this is where you can play with a small heater, large storage tank, large heater, small storage tank, depending on how you want to approach it, and depending on how much room you have in your mechanical room. Okay, if I look at this example, sidearm heater with a storage tank, total for the heaters in the tank, I'm in at about $35,000. Let's look at tankless. Okay, what's unique about tankless, at least with IntelliHot, the set point doesn't matter as much as the fixture temperatures do. Okay, so this one's critical. Obviously, incoming and fixture temperatures are driving the selection. In this case, we need 35 gallons of hot water. It's going to equate to about a 1.5 million BTUs, or in our case, an IQ 1500, which is about $67,000 to go tankless. No storage tank. We could look at a air source heat pump style water heater. Peak or off peak, if you will, is going to be 8 hours. If you remember from our example, in our case, we're going to be looking at a load of about 134,000 BTUs during that off peak time. And what's important here is the storage required is about 1,300 gallons. So heat pumps don't generate a lot of hot water. So they need pretty good sized storage to maintain that throughout the day, depending on your loads. So here we've got two heat pump water heaters and 1,300 gallons of storage, designing for about a 40-degree worst case outside air temperature. We look at some numbers here. We're in at about, excuse me, we're in at about $71,000. So let's summarize this. Non-code tank type water heaters, $40,000, individual venting, 3 to 5 year warranty. Okay, if I go with 2 condensing and a storage tank, I'm in at about 35,000, 5-year warranty. If I go tankless, probably takes up the least amount of floor space, 67,000 with a 10-year warranty. And if I'm going air source heat pump, 71,000. The most storage at 1,300 gallons and a 5-year warranty. So we got 4 choices. How do you narrow this down? Well, I can help you if decarbonization is on your forefront and we can't fire natural gas. We might lose 3 out of the 4. Your tank type might go away unless you want to go electric. Sidearm is going to go away. Tankless is going away. And your only option might be a heat pump water heater. Okay, depends on your application. Depends on whether you have natural gas available or not. But if you're in a decarbonization zone, you might have some limitations as far as what you can use for water heaters in general. Something to think about. Okay, quick summary. And I think we're wrapped up. How are we doing on time? I went a little long. I apologize.
Just barely. All right. Any questions? Don't see anything at this point.
This is fantastic. I won't. Oh, do we have some questions coming in?
No, it's just thank you and no questions for me. You know who that
A
is.
quick comment that came from Tuesday, and that's the difference between non-ASME and ASME tank type water heaters. If you look at a manufacturer's, if you get a chance to tour a manufacturer site, it's fascinating. The non-code, nothing's really categorized. It simply comes in, runs through the production, gets on a truck, and off they go. ASME tends to be a whole different section of the shop or fab facility, and everything's categorized by materials. That you've got dedicated welders on site, and you also have an inspector that has to sign off on all that before it can ship after it's been pressure tested. So definitely a big difference in criteria between non-code and ASME code on the water heaters.
We did have a question come through, Paul.
Sure.
Can you explain more or better the difference between condensing and non-condensing boilers?
No, because this is water heaters and we're not talking about boilers. Let me give it a shot. Now, yes, I think I can. It's all based on return water temperature and materials of construction. Now, I might need to break out of this Sunday as my only. I don't know that I have anything great here to address that. Okay. Let me stop this for just a second. If anybody wants to hang with me, great. Let me open up another presentation real quick because I think that's where I need to go. So hang tough. Let's see if I can get there within a short amount of time. And Sunday I'll reshare in just a minute. Let's try this.
No problem.
Share screen. Let me just share that guy. And we want to talk about condensing versus non-condensing. Here's my efficiency charts. Oh, here we go. This might be the best one to look at. And this is boiler. Sunday, are you seeing this okay? Does this work for everybody?
Yep.
Okay,
all
perfect. Good. So the thing to keep in mind with all manufacturers, and this is just an ASHRAE chart that's based on return water temperature, but it does show very clearly the difference between condensing and non-condensing. Okay, if you're a condensing product, it means your materials can handle low return temperatures. And low return temperatures means we're taking some moisture out of the products of combustion. That's very acidic. So typically you're dealing with stainless steel construction in order to deal with that. So a condensing boiler or water heater, you're looking for the coldest temperatures you can get to maximize your efficiency of that product. Okay, so basically you're sending less heat up your flue or your stack, which makes your boiler or water heater more efficient. If you're non-condensing, your materials of construction can't handle the acid you would get with low return temperatures. So now you're limited on that return temperature that that water heater or boiler can handle. So typically for most manufacturers, that's about 130 degrees. If you're cast iron sectional, it's about 140. But if you're non-condensing, make sure you read the O&M because it's going to tell you what that minimum return temperature should be and not go below. Okay. It's all based on efficiency, but a lot of that has to do solely with return water temperature and the materials of construction. I hope that helps answer the question a little bit. If not, shoot us an email. Happy to address that further. Okay.
Any other questions? I don't see any coming through, Paul.
I know you're ready to go Sunday.
Everyone's
you're ready to just
taking
pull
naps.
the plug.
I'm like, I'm out.
As
No,
Sunday said,
I'm
we
good.
appreciate everybody and thank you for sticking with us, our little sixth sense of humor here. But yes.
Yes, we appreciate all of you. Thanks so much. As always, if you have any questions, please feel free to reach out to myself and I'll forward them to Paul and then he can answer them for you. But we're always here for you. So please reach out if there's anything that you missed, if there's a class you missed that you wanted to take, or you know, you just had questions and needed to get into some more detail on something that Paul taught. We're always available and I can always send you any recordings that you need. Like I said, this recording will be sent out next week and we hope to see you in the future at our next sessions.
Awesome. Thank you,
All right.
Sunday.
Thanks everyone.
Everybody.